Okay, welcome to the next lecture. So we left you last time, we'd been looking at activity on the sun driven by the differential rotation and the convection, stirring up the magnetic field. So I left you with an exercise looking at the differential rotation. So we had considering two sunspots, one equatorial that was had an orbit of 27 days, and a higher latitude one with an orbit of period of 30 days. So here's a rough sort of way of looking at it, so that the higher latitude spot lags the equatorial one by 3 days, which is 1/10 of its orbit. So therefore you're going to need 10 orbits in effect before the overtake happens. So that's around 300 days. If you want to be a bit more accurate and formal mathematically about it, you can use circular motion. I'm not going to go through this in any detail, but you can use circular motion equations here to, again, look at the idea of overtaking, and that gives you an answer of a more accurate answer of 270 days. Again, not too worried about the number here, it's the principle. So over the period of nearly a year or so, you can see that the sun is wrapping itself up because of this differential rotation. Okay, so as you can see from the this week's backdrop, then we're moving on now, and we're going to start to talk about stars in general, and we're going to start with some basics about looking at the radiation from stars, and in particular we're going to talk about what I will call the continuum spectrum. So this is the broad band color of light coming from stars, and we're going to introduce the concept of black body radiation, which is extremely useful, and then two things that flow directly from that: Venns displacement law and concepts of luminosity and flux, and how that's related to the temperature of the star. Okay, so again, we'll start with the sun as an example of a star, since that's where we're coming from, and it's obviously familiar to us. So if you take sunlight, exactly as sort of Isaac Newton did, put it through a prism and split it up and look at how the intensity varies as a function of wavelength, that you get a spectrum of the continuum radiation from the sun. And if you look at where that peaks, it's around about 500 nanometers, so right in the middle of the sort of optical spectrum. Now, if you then sort of further analyze the shape of that spectrum, then you find that it's very close to this idea of what a perfect black body would radiate as if it had a temperature of just under 6,000 Kelvin. So you remember when we talked about the photosphere of the sun, we talked about it having a temperature of around about 6,000 Kelvin, so it's just under at 5,800 Kelvin. Okay, so what's this idea of a black body? So a black body is it's a theoretical concept with an analytical equation, just a formula. And here in this diagram from the universe textbook, you can see the two things superimposed. So we have a spectrum. So here it's marked as intensity. I would perhaps more formally call it flux, as we'll see a bit later in this lecture, against wavelength. So here is the sort of optical regime, centered, running from 400 to 800 nanometers. And you can see that the black curve here is a representation of the observed spectrum from the sun. And so you see it peaking here, sort of in the sort of yellow-green part of the spectrum, okay, which is why the sun appears yellow in the sky. Superimposed on here, you can see a red curve. So this is a smooth curve. It's just an analytical function, and that curve is what we would call a black body curve at a temperature of 5,800. And you can see it's a pretty good representation of the shape of the spectrum of the sun. It's not perfect, okay, so there are discrepancies here, some features here in the sun spectrum, but overall it does a pretty good job of representing the shape, especially at this the redder end. Okay, so that's what we mean by when we say that the spectrum from the sun, and in fact all stars really, can be represented quite well by a black body curve. So what's this idea about black body radiation? Some of you may have come across this idea before, some of you may not have. So a black body is a theoretical concept, basically. So it's the idea that you could have an object that was a perfect absorber of radiation, and that's where the name comes from. Okay, so I'm sure you're aware, if something is painted black, it basically doesn't reflect any light, which is why it appears black. Okay, so a perfect absorber would be in effect sort of perfectly black. It would absorb every single wavelength of radiation falling on its surface, and so that is where the concept starts, that it will perfectly absorb radiation. But of course, everything has a temperature, and anything that is above 0 degrees Kelvin will also emit radiation. And so if you sort of invert that concept of a perfect absorber, you can also get the concept of a perfect emitter as well. So that it would perfectly emit radiation commensurate with whatever temperature the object actually is. So that's in a nutshell, that's the idea of black body radiation. And this emerged from quantum physics, and so the analytical formula that describes black body radiation is referred to as the Planck function. Now, if you want to go and have a look at the sort of more mathematical aspects, that's totally optional. If you're interested in that side of things, go and have a look at the handout on the Minerva site for this lecture, and there's a document there that will show you what the analytical function for the Planck function, which describes the intensity of radiation emitted by a black body, is. But that's not part of the module. You won't be required to know that or be tested upon it at all. Okay, so it's there for background information for those of you who are interested in the sort of mathematical side and want to make links to other areas of physics, etc. Okay. Now, in terms of, I've got to put this diagram here. In terms of, again, perhaps trying to build up that idea of what a black body physically is, you can get quite close to recreating a perfect black body in the laboratory. And what you would do is illustrated here. You could take a sphere, okay? You could paint the inside of it perfectly black. I mean, that's tricky for a start, obviously, if it's totally enclosed, but that's why it's conceptual. So you can never quite attain it, but you can get close to it. So if you paint, find the blackest paint, if you like, that you can possibly find and paint the inside of the sphere black, then you take the whole thing and heat it up. So you would uniformly heat the outside so that the whole sphere, put it in a heat bath, basically the whole sphere was at exactly the same temperature everywhere, okay? And then if you obviously want to observe the radiation field that's generated by that sort of situation inside the sphere, but you can't put yourself in here, so you have to cut a little hole to let the radiation out and observe it. And so that's illustrated here. So if you then looked at the spectrum of radiation coming out of the little hole in this uniform temperature, perfectly black sphere, it would be pretty close to what is described by the Planck function for whatever temperature you'd heated it up to. Okay, so that's the idea of a black body in the lab. And so effectively, we're thinking of the sun as this very uniform sphere with a uniform temperature all around it. which is emitting pretty close to that of a black body. Okay. So there's two extremely nice things that flow from the idea that a star is emitting like a black body. And the first of these is Venns displacement law. Okay. And this is to do with where the peak of the emitted spectrum from a black body occurs, and at what wavelength does that peak in the black body curve occur. And it's given by a very simple formula that only depends on the temperature. Okay, and so it's given by this simple formula here. So this is probably the first key formula that we've had in the module. So this one is one you will definitely need to know and use throughout the module. We come back to this time and time again. Okay. So basically, all you need to do here is put the temperature in Kelvin. Okay, this is a constant, 3 times 10 to the minus 3. And then the wavelength, the peak wavelength, lambda max here, will come out in meters. Okay. So again, everything in the formula in this module should be in SI units, unless I tell you otherwise. Okay. There are some formulae that are non-SI, but I'll alert you to those when we come to them. Okay, so this basically tells you that the hotter the body, so the higher T is here, the peak wavelength will move to shorter and shorter wavelengths. Okay. And that's illustrated on the next diagram here. Okay. So here we've got a very similar diagram, but this time you've got 3 different black body curves on here. So these all stem from plotting the Planck function for different temperatures. Okay. And you can see the 6,000 one here is peaking, in the middle of the optical regime, just very similar to the sun as we had before. If you increase the temperature, the peak moves to short wavelengths. So if you double the temperature, like here, your peak is going to shift down to about 250 nanometers, which is in the ultraviolet part of the spectrum, so off the blue end of the visible spectrum here. And if you half the temperature to 3000 Kelvin, then the peak of the black body function will move, will double up to around about 1 micron in this case, 1000 nanometers. Okay. And these temperatures are quite useful for setting the scene for where we're going. 3000 Kelvin is about the coolest sort of type of stars that you ever get out there in space. The sun at 6,000 is a very average sort of star, as I've mentioned, and you do get hotter stars, as we shall see. So you can certainly get stars up at 12,000. In fact, you can get them up at 30 or 40,000 Kelvin. So this illustrates the sort of range of peaks that you will get for different stars of different temperatures. Okay. And you can immediately see from this that cool stars will appear red, effectively, because their peak is down here and more of their emission is in the red end of the spectrum, whereas very hot stars will appear blue to our eye, because most of their output will be up here in the ultraviolet. And if you look at the my background picture around me here, you can see this already. You've got red stars, and blue stars, and ones that are in between. And that's immediately telling us about their temperature. Okay. So perhaps just another analogy to illustrate this idea of Venns displacement law. If you've ever got to do any metalwork at school or college, or if you've ever visited a blacksmith and watched someone heating up an iron bar in a furnace, that iron bar will start off by glowing a dull sort of red color, and then as it gets heated up, it will basically move through the colors of the rainbow. It will go to sort of orange and then yellow, and then eventually it will become this kind of, basically people would say white hot, but in effect it's coming up here to the more blue end of the spectrum. It will never appear actually blue, because you've got all the other wavelengths as well, so it appears white. Okay, but that movement from dull red color through orange and yellow up to the white heat is an exact example of Venns displacement law. The solid iron bar, as it's heated up, is emitting very similar to a black body. Okay, so that's the concept. Right, let's have a little example that I've done for you here, just so you can see this formula in action. Okay, so let's just do it for the sun. Okay, so let's put in a temperature of 5,800 Kelvin, and then if you evaluate that, you end up with 5.2 times 10 to the minus 7 meters. And if we put that in sort of the traditional units used for the optical spectrum, optical wavelengths of nanometers, then that's 520 nanometers. And so obviously that's exactly what we just seeing. The peak of the sun here is just over 500 nanometers in the middle of the optical spectrum. So that's Venns displacement law in action. Again, for those of you who are interested in where the law comes from, you can actually prove it to yourself if you like looking at the maths. So if you go and look at the Planck function, you know, you've got this smooth curve here. Basically, you're asking yourself, how do you find the peak of the curve? Okay. And so if you remember your A-level mathematics, then to find the peak in any function, you need to differentiate it and set the gradient equal to 0. Okay. So if you look at the Planck function, which is basically, it is only a function of temperature and wavelength. It's got two variables in it. Okay, so for a fixed temperature, you differentiate with respect to wavelength, set the gradient equal to 0, and solve for what wavelength that is, and that's where that formula for lambda max comes from. It's just the maximum, the peak in the black body curve. Okay, so that's Venns displacement law, what it means, where it comes from. Okay, so there is a second concept that comes out of black body radiation. So here we're now going to look at what the sort of total amount of energy emitted by a black body is. Okay. And so that's really coming from the area under the curve here. And that will bring us back to this concept of luminosity. So here we're asking ourselves, what's the luminosity of an object that is emitting like a black body? Okay. So again, there's a nice formula that comes out of this, and again, this is key to underlying much of astrophysics. Okay. So the total power in the radiation from, we're going to set up an object with a radius r, and it's got a uniform temperature T. Obviously, it's representing a star, really. Okay. And asking ourselves, what is the total amount of energy per unit time? Okay, so power, effectively. That's what luminosity is, joules per second, or watts. Okay, and it's given by this simple-looking formula here. So you've got this term 4 pi r squared, and then you've got this other term, sigma T to the 4th. Okay, so where T is the surface temperature of this sphere with a radius r. And we've got this constant here, sigma. That's called the Stefan-Boltzmann constant. And it's actually an amalgamation of lots of other fundamental constants if you want to go and look at the theory. But this is all we need for now. Okay. Hopefully you recognize this term here, 4 pi r squared. That would basically be the surface area of your sphere. Okay. So 4 pi r squared is the surface area. And so you can think of sigma T to the 4th is really the amount of energy per unit time per unit area being emitted by this sphere. So you just scale up by the area of the sphere to get the total luminosity. Okay. So you can see here that this is a useful concept. Okay. So basically the total amount of luminosity of a star will be given strongly as a function of its temperature. So hotter stars are emitting much more radiation, much more energy. And obviously bigger stars of a given temperature will also emit more energy because you've got a bigger area from which to emit from. So hopefully that makes sense. Now, when we apply this to stars, we can come back to this question a little bit that I touched on when we were discussing sort of the atmosphere of the star and the idea of where is the surface. So in stellar astrophysics, then we often talk about what's called the effective temperature of a star. So this is another way of expressing this concept of the surface temperature of a star. Okay, and so we can use this formula to sort of define, in effect, what the effective temperature of a star might be. So it's defined as the surface temperature that a spherical black body would have with the same radius as the star, and that would provide the star's luminosity. Okay, so if we knew the luminosity of a star and we knew its radius, then we could work out the effective temperature of the star that way. Now, if you think about this for a moment, then it's a different way of looking at the same problem. Remember, there's no solid surface, there's no well-defined edge. And so what we've really done here is just shift the problem from worrying about where we define the temperature in the photosphere to where we define the radius of the star. And of course, that is also quite tricky, a concept. I mean, when you look at an image of the sun, you can see that it's got a sharp edge because of the way radiation interacts with the material in the atmosphere of a star. But defining exactly what the radius of a star is also a little bit tricky. So you've only shifted the problem from defining the surface temperature to defining the actual radius. But still, this is a very useful concept that we can use again and again throughout the module. Okay, so this is another important formula. So to finish up this first part of the lecture, I'll leave you with a little exercise to put that formula into operation. You'll need to go and look up the Stefan-Boltzmann constant, obviously. So obviously you know what the answer is here, but make sure you can see how that formula works and that you recover the effective temperature of the sun, given that its radius is 7 × 10⁸ meters and its luminosity is 4 × 10⁻26 watts. Okay, so have a go at that, and I'll see you on the other side of the break.